Hello young little minds, welcome to All Force e-learning program. This is physics session number 41. Now in this session we shall discuss about the effect of the metal conductor in an electric field. When a metal conductor is placed in an electric field, what effect does it show? What properties we can understand, right? So the effect of the electric field on a metal conductor. When a metal conductor is placed in electric field, what are the various points we can understand, right? We'll know about this. So before going to this, let's have a recall of what are the necessary things to study to understand this. So charge, fundamental property, charge produces field. Now when you consider a charge, this charge exhibits its effect, its property in the form of lines of force around it. So around the space of the charge, it shows its effect by producing lines of force within the vicinity there. So the space around the charge where the influence of the charge can be experienced, the effect of the charge can be felt, that space is electric field. So always remember, wherever there is electric field, there are lines of force, electric lines of force. So electric lines of force, different types: uniform electric field, non-uniform electric field. If it is a uniform electric field, then the lines of force are parallel lines. If it is a non-uniform electric field, lines of force are either diverging or they are converging. They move apart or they come closer. So curved lines, different types of electric fields. And every electric field has a strength, that is electric field strength, electric field intensity. It is the force experienced by unit charge, right? When you place a charge in the field, what force does that charge experience? Now, that is the strength of the field. Well, later then flux, every charge now produces lines of force. I was telling you, charge produces lines of force. The count, the measure of number of lines of force passing through a space. If I consider a space, what number of lines of force pass through, that is actually called electric flux. Well, flux density, electric flux density, flux per unit area. We have been learning all these things, right? So the flux is E by A. So flux density is E is equal to phi by A. So flux phi is E into A, E dot A, EA cos theta, right? The small flux for uniform electric field, the flux is E dot A. Right? Then if the angle is same, then it will be EA. But for non-uniform electric field, the small flux is E dot ds. So the total flux is integral of E dot ds. It's integral E dot ds total flux. Right? So this way it is. Electric field, there are lines of force. Now let us understand what will happen when I place a metal conductor in a electric field. Right? Now, consider a metal conductor. Let me imagine a metal block. Let me consider a metal block. Suppose this is a metal block, right? A metal block. Now it is placed in an electric field. I am placing this in a uniform electric field. Let's say uniform electric field, okay? There is no such compulsion that you have to take, it can be any field. So let me take a uniform electric field. You know, I was telling you, uniform electric field is produced by parallel plate capacitor. Two metal plates charged positive, this is positive metal plate, right? Two parallel plates like this, charged equal and opposite, this is positive, that is negative, like this. Then the lines of force are parallel lines like this. The electric lines of force due to these are parallel lines. Now I was telling you parallel lines produce uniform electric field like this. They produce uniform electric field. That is, the electric field is constant at every point. The magnitude and direction of the electric field is same at all the points. Now, so I am producing a uniform electric field. In that uniform electric field, I place a metal block. Now what happens? Whenever, as and when you place a metal block in the uniform in the electric field, Then metal has many free electrons, abundant number of free electrons existing in it, available at room temperature. So as and when I place this metal block in this one, those free electrons momentarily experience force, right? And these electrons experience force and move. They get polarized, they move. Now the electrons experience force. Suppose if I consider an electron there, then this electron is attracted by this electric field. Let the electric field be E, then E naught, let us say. Then the electron is attracted by the positive charge, repelled by the negative charge. It experiences force in the opposite direction, right? F electron is equal to minus E into E. It experiences force in opposite. So this way all the electrons, as and when you place the metal block, the electrons there experience force momentarily, and all the electrons get deposited on one side. The negative electron, all the electrons get deposited on one side. Well, the opposite positive ions go and get deposited on the other side like this. Then it stops. The movement of the electron just takes place for some time, and momentarily there is motion, then later they just stop. Now the charges are in electrostatic equilibrium. Now they are in EM. They just move. So as and when I place the block in the electric field, the lines of force influence the field, the electrons, and the free electrons momentarily move, get deposited, then stop. So what do you mean stop? Stop in the sense they are now in electrostatic equilibrium, the force. So when I was just placing the box, as and when I place the box in the field, at that instant the electrons experience force, they move, get deposited at one place, then stop. So in the sense the net force has become zero. The electrostatic equilibrium is maintained. Now there is an electrostatic equilibrium. How? Let us consider the electric field produced by the capacitor plates. The external electric field is E naught. Now what happens? Inside the metal block, the electrons have got deposited on one side and the positive ions on the other side. Now these positive negative ions produce an opposite electric field. An opposite electric field is induced on the opposite electric field is induced inside the metal field. The negative electrons have come and deposited on one side, positive ions on the other side. These positive and negative ions, they produce an opposite electric field, and this electric field is induced electric field, right? Now if I consider any electron, free electron somewhere existing in between, due to the external electric field, that is E naught, it is attracted by the positive charge, it experiences force in this direction. So force due to the external electric field is in this direction, let's say minus E naught into E. Now the same electron experiences force due to the induced electric field that is produced inside the metal. So the electron experiences force due to the induced, inside the metal there is induced electric field in opposite direction. Now this electron is repelled by the negative charge that is deposited here, attracted by the positive charge deposited here. So it experiences force due to the induced electric field that is in this direction. It's plus EE. So now the net force on the electron, net force due to the external field plus force due to the induced electric field, that is minus E naught E plus EE is equal to 0. So minus, this is in opposite direction, minus E naught E, this is plus E induced. Let us say induced electric field is I E induced. So therefore net field is 0. If I take it that side, induced electric field into E is equal to minus that side, so it is E naught into E. So the induced electric field is equal to E naught. Well, the magnitudes are equal, direction is opposite. So inside the metal, so what happens? Whenever a metal is placed between the plates of a capacitor, or it is placed in an electric field, then for a small tiny moment the polarization of the charges take place. Negative charges get influenced, just move, deposited one side, positive ions move to the other side, then get polarized, then later they stop. So momentarily there is motion and later they come into rest. So now finally they come to electrostatic equilibrium. Now equilibrium in the sense the net force is 0. Now how it is 0? So this way it is. So later, after the adjustment takes place, distribution takes place, adjustment takes place, then if I consider any other electron in between, some electron. The electron that remains somewhere in between, it is yet to experience the force due to the electric field, for example. Then on that, the external electric field applies a force, attracts, the external electric field attracts the electron in this direction, minus E naught E. But inside the metal, when the charges get relocated, electrons move on to one side, positive ions move on to other side, electrons move to the side where the positive charge of the external electric field exists. The positive ions move to that side where the negative charge of the external electric field exists. So therefore, these electrons come on to one side, positive ions on the other side. These positive negative induced charges, now they produce induced electric field inside the metal block. So they produce an induced electric field. That electric field is in the opposite direction. Now if I take any other electron in between, then this experiences two forces. Force due to the external electric field and force due to the induced electric field that is produced inside the metal conductor. Force due to external electric field. Well, the external electric field has got positive charge here. Electron is attracted by the positive charge. Force due to external electric field is this side. Now force due to induced electric field. Now induced electric field, it is in this direction. So both the forces maintain the electron in equilibrium. So I said, as and when I place the block, the electrons just get displaced and later they come into equilibrium. They momentarily get stopped. They just move, relocate, arrange themselves, right, then stop. So later when they stop, the net force becomes zero. So sum of these two forces is equal to zero. So the sum of external force and force due to induced field, force due to the external field and force due to induced field on the electron is zero. So that is external field force this side, left, so it is minus E naught E. Right side, right, if I write in vector form, for example, let me show this in vector form. We don't know, let us not take the direction. Force due to external field plus force due to induced field is zero. Force due to external field, that is external field E naught into E, that is minus E of course, plus force due to induced electric field, that is E induced into minus E is 0. Well, minus common, E external E naught plus E induced into minus E is 0. Well, electron charge cannot be equal to 0. So E external plus E induced is 0. When I take this, so E induced in vector form is minus E naught. So inside the metal, an equal and opposite electric field is induced. So that is E induced is minus E naught like this. Because of these two fields, now the charges inside experience no force. They experience no force. What does this mean? They experience no force in the sense, at any point inside the conductor, the net electric field is 0. So the resultant force on the electric electron, it is the resultant electric field into charge of electron. But the resultant force on the electron is 0. So the resultant electric field into charge of electron 0. Electron charge cannot be 0. So the resultant electric field is 0. So therefore the field inside the conductor is 0. There is no net field inside the conductor. The net field inside the conductor becomes 0. So when I place a block inside the electric field, in an electric field like this, then the charges are induced. The charges are induced such that they remain on the surface. Inside the conductor, the net electric field is 0. Right? So there exists no electric field inside the conductor. So obviously when the net electric field is 0, the flux, if I imagine a Gaussian surface inside a conductor, the net flux coming out of this Gaussian surface, the net flux is integral E dot ds. So therefore net flux is integral E dot ds. Well, at any point the electric field at any point is 0 inside, so the net flux is 0. According to Gauss law, we know that total flux is charge enclosed inside by epsilon naught. So therefore, if I apply Gauss law, if I imagine a Gaussian surface this way, apply Gauss law, then the net charge that is inside the Gaussian surface, right? Since net flux is equal to 0, I have just now proved. So charge inside by epsilon naught 0. So charge inside is also 0. So the net charge inside the metal conductor will be 0. So therefore, whenever you place a metal conductor in a electric field, now what happens? Whenever you place a metal block in a electric field, then at that instant, momentarily there is a relocation of the electrons experience force. They polarize, they get deposited on at the ends. Electrons deposit at one end and the positive ions at the other end. Then they all remain stationary. They all come to rest. So there is equilibrium. They stop. Right? They are in equilibrium. Electrostatic equilibrium. In the sense, the net force that is experienced by the electrons becomes zero. The net force becomes zero. So net force zero in the sense, initially when I was just placing the block, there was force. Now later it has become zero. In the sense, there might have appeared an opposite force which is balancing the force due to this. When I have placed that metal block when I just placed the metal block in that electric field, at that instant, at time t0, at that time 0, the electrons experienced force. But later, the force of the electrons has become zero. Now, how come initially there is force, later there is no force? In the sense, initially, as and when I place the block inside the metal conductor, initially the electrons get influenced, free electrons get influenced by the external field. Now, as and when the metal block is placed in the external electric field, now the electrons momentarily are in motion. They just move. Then they relocate. They arrange. They move. Electrons move to one side, positive ions onto other side. Then after that, the remaining. Then all the charges come to equilibrium. There exists a state of electrostatic equilibrium. So initially there is force, but later it is zero. In the sense, in the process of this relocation, in the process of this rearrangement, there is a field that is induced inside the metal block which will balance the external field. So as and when I played the metal block, the electrons were experiencing force, but later the force has become zero. In the sense, after the relocation or redistribution, there is a field that is induced inside the metal block called induced electric field. Now the electrons are under the action of two fields, the external electric field and the induced electric field. So the external electric field attracts the electron in this direction, and the induced electric field, induced electric field is from this side to this side, opposite to the external. The induced electric field is in the direction opposite to the external electric field. Now the force due to that is in this direction. The net force becomes zero. In the sense, so what do you infer? Whenever you place a metal block inside an electric field, then an electric field is induced inside the metal. Then an electric field will be induced inside the metal, which is equal and opposite to the external electric field. Equal and opposite to the external electric field, right? So the net electric field inside. So inside the metal conductor, the net electric field becomes zero. What do you mean net electric field becomes zero? We know the total flux is integral of E dot ds. When the electric field is zero, the net electric field intensity is zero, then the flux is zero. So inside the conductor, when you imagine a Gaussian surface, the flux emerging from this, the total flux emerging from this becomes zero. So there is no field inside the conductor. So the total flux inside the conductor becomes zero. In the sense, right? So when the field inside the metal is zero, suppose if there is an external magnetic field, external electric field like this, I am placing a metal conductor inside the metal conductor in the external field. Then the electric lines of force, they go like this. Now inside this, the resultant electric field is zero. In the sense, inside, if I imagine a Gaussian surface like this, then inside the Gaussian surface, the total flux coming from the Gaussian surface will be zero. In the sense, according to Gauss law, what is the flux? The total flux from a Gaussian surface is proportional to the charge enclosed inside. So when the total flux is zero, so the net charge inside is zero. So there is no net charge that is contained inside the metal conductor. Net charge is zero. It does not mean there is no charge. There are equal and opposite positive charges in every element. Take any space, in that space the number of positive charges and the number of negative charges will be same, right? When a metal conductor is placed in an external electric field, then the net electric field at any inside point is 0. If the net electric field is 0, so the net flux through a Gaussian surface, imagine any Gaussian surface inside the conductor, so the net flux is 0. So if the net flux is 0, implies the charge inside the conductor, the net charge inside the metal conductor is equal to 0. So in the sense, the net charge inside the metal conductor is 0 implies that suppose if I take a metal conductor like this, way, placed in an external electric field this way, then so inside, at any inside point, the resultant electric field is 0. So electric field inside 0. So the flux is 0. So the charge inside is 0. In the sense, the charge whatever that is given to this will reside only on the surface of the metal conductor. No charge will reside inside. All the charge will be existing on the surface of the metal conductor. Suppose, imagine that there is a metal conductor like this. I give a charge. When I give like charges, these like charges repel one another and they move to the extremities. They stay on the surface. So all the charge resides only on the surface. The charge inside the conductor is always equal to 0. Right? Even if you place it in external field, no charge will reside. If there is any charge to be if there is any charge that has to come, then it will exist only on the surface. The net charge inside will be 0. And one more thing, suppose if the metal produces a field. So first point, when a metal conductor is placed in electric field, the net electric field inside the conductor is 0. The net flux inside the conductor is 0. The net charge that is residing inside the conductor is 0. So if you give charge to a conductor, any charge, like charge, you are giving like charges, positive. The very next positive charge will get repelled by this. They go to the extremities, stay on the surface. Even for the negative charge also, you are giving negative electrons. So suppose if you are transferring electrons to this metal conductor, first electron will get inside. Then when the second electron gets in, that electron is repelled by the first one. So they go to the extremities. As you give charge, they are repelled by one another. So they move on to the extremities, stay on the surface. The net charge inside is 0. Net flux. So net flux inside the metal conductor is 0. Net charge inside the metal conductor is 0. Net electric field inside the metal conductor is 0. Then how about the electric field on the nearest point of the surface? Now the electric field on the nearest point on the surface, suppose if this is positively charged, right, then the electric field here will be sigma by epsilon naught. The electric field at the nearest point on the surface is sigma by epsilon naught. It is independent of the shape and size of the conductor. It is independent of the shape and size, but the condition is the surface charge density of this must be very much high. It is heavily charged, a strong charge, right? If the surface charge density is very much high, the charge existing per unit area is more, then the electric field at the nearest point to the conductor is always a sigma by epsilon naught, right? Independent of the shape and size, but the condition is the charge should be strong, more, the amount of charge should be more, like the surface charge density should be more. Then the electric field at the nearest point is always, right, is sigma by epsilon. And also the direction. The electric field at any point on the surface will be outward normal like this. Here it will be outward normal. The lines of force will emerge. The lines of force normal to the surface like this. They emerge normal to the surface this way, right? So the lines of force are always normal at any point on the outer surface like this. The electric lines of force are they emerge perpendicular to the surface at any point. It is whatever be the shape, at that curved surface, the direction of the electric field will be normal to the surface. In the sense, tangential to the surface, the field is zero. There is no component of the electric field parallel tangential to the surface. The component parallel to the surface is zero when it is given charge. When it is given charge, then the lines of force emerge normally perpendicular. The component of the electric field tangential to the surface will be zero. Along the surface is zero. Lines of force exist perpendicular to the surface. So whenever let us come on all the things. Whenever a metal conductor is placed in an external electric field, then electrons momentarily move for some time, small time. They relocate, rearrange, get polarized. They get deposited. Electrons get deposited on one side, positive ions on the other side. Then they come to rest. There is electrostatic equilibrium. In the sense, when external electric field is applied, then there is an equal and opposite induced electric field inside the conductor. So whenever a metal conductor is placed in external electric field, an electric field is induced inside the conductor which is equal and opposite to it. As a result, the electrons inside experience no net force. The net force becomes zero. So equal and opposite electric field will be induced. The net electric field inside the metal conductor is zero. If the net electric field is zero, the net flux emerging at if I imagine a Gaussian surface inside, the net flux emerging from that will be zero. So if the flux is zero, according to Gauss law, the net charge inside the conductor is equal to zero. So there is no charge residing inside the conductor. Then all the charge, suppose if you give charge to a conductor, then what happens? All the charge exists only on the surface of the conductor. No charge will be residing inside the conductor. Charge exists only on the surface. And at any surface, if you consider at the nearest point, the strength of the electric field is sigma by epsilon naught. And this will be perpendicular to the surface. The field will be perpendicular to the surface, normal to the surface. Tangential to the surface, the electric field is zero. There is no component of the electric field along the surface, tangential to the surface. The electric field is normal perpendicular to the surface. Okay, thank you.